I need wire. I did the whole cookie in 5 minutes. I have a. I'll get started. Oh. I don't think you want. You could put it all right at that point. Yeah. For that, going to where would be like keeping it still, right? Keeping it mounted, making sure like that the breakover for the. Yeah, the reference point, you just in on the spot, you're not being around. If it's fluid. Yeah. That was all pretty just for just in case, just keep the ones go like it fall like that and then it goes like that. Yeah. Like, yeah. It's just stand off, it's stand off and then. We like.
How's it going? All right. Almost there. Got 2 more weeks of class and then finals. You're walking this year, right, Augie? I'll see you at your graduation then. I'll be there.
Question on the last exam, that question I was asking about what might make explicit method right?
Yep.
Was it because you have a small time step?
It's too big.
Too big.
Yeah.
I got that wrong.
Yeah, I graded on Friday. If you're small, you make the time step. It's just like the mesh. So the smaller you make delta t, it's like same like delta x, then it's more accurate and it gives you less cost. Yeah, I got some of that on the exam too. For time marching, it's a little bit more complicated. There are numbers like that. They're just not as reliable, I guess. And like the method that we're using, explicit, implicit viewer, those really aren't used in practice just for they're mostly pretty simple. So most solvers use more complex things that have their own numbers and stuff like that. That's why no one really tracks it for time marching.
Okay.
I'll fade over. Yeah.
Okay, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Doing good. Question. So question, is homework 6 the last homework assignment? I remember you saying there would be 7. Yes, homework 6 is the last homework assignment. The 7th homework assignment was homework 0. And so if you start counting from 0, then there was 7. Yeah. Yeah, so after homework 6, there's that's the last. And of course, the final project is that. Okay. All right, and so announcements. All right, so I've graded the midterms, and so I have them here with me today. So you guys will be able to pick them up after class today. And so the average was good, a little bit lower than the first exam, just because this content is harder. So naturally, the average is going to be lower, but still 39 out of 50. So very solid average for the midterm. So definitely, come by, pick it up. If you have questions about how I graded it or questions on the solutions, just let me know. And then we can go from there. All right, and so we are very quickly, we are on the last 2 weeks of the semester, so we have 4 more class sessions. And so I think, at least for me, I think I'll have probably 3 more lectures worth of content. Mostly, we're basically winding down at this point. So we have about a class session talk about higher order schemes with finite volumes. And then we may be able to start unsteady problems in finite volumes. And then, we'll wrap up after that. Okay. So next week, so the plan for this week, I think, we're gonna have lectures just as usual today, Monday and Wednesday as well. Next week, I'll probably finish up all the content for the class on Monday, maybe probably halfway through the class on Monday. And then for the rest of class on Monday and for next Wednesday, I thought I'd just have kind of this open workshop, because I know you guys will be working on the final projects. And so if you guys have any questions on the code, if you have any questions on how to get started on the report or anything like that, you can bring that to class next week, and then we kind of work on that together in class. Okay. So remember, the final project's not due until after finals week, and so it's due the Monday after. I believe that's like the 19th or something like that. But I would definitely recommend you getting at least started on the code this week, so that you can come to class next week with questions. So all throughout finals week and all the way up until it's due, I'll still be answering questions, and we can set up office hours and make appointments and stuff. But kind of the easiest time to get a hold of me is during the lecture times. And so, if you guys start by next week, then you can ask questions and, hopefully get a good jump on the project before we head off for finals week. Okay. All right. So that's all for my announcements today. Are there any questions I can answer before we get started? Okay. All right. So let's go and get started. And where we left off last week was higher order schemes and finite volumes. Okay. All right. So last Wednesday, we started talking about this idea about higher order schemes. Right? And the whole idea behind higher order schemes is that, whenever we have a problem that has convection, convection usually causes a lot of issues. Right? Okay. And that's kind of why, computational fluid dynamics or CFD is just challenging in general because fluids is nothing but convection. Okay. And so, we're not quite at the point of CFD yet, but, we are seeing some CFD like effects or CFD like problems, I should say. Okay. And so basically the idea is that when we approach convection with our basic schemes, some issues could occur, some things like stability, we could have unstable solutions, or we may have, some other issues like cross-stream diffusion. Okay. And so the idea with this unit is that, we can change how we simulate the convection term to get around these challenges. Okay. Because so far, all of the other methods that we've gone over, they kind of have a cost, right? And so, even before, this goes kind of way back to kind of more the beginning of the semester. When we talk about upwinding schemes and we use our forward difference or backward difference, that was one way that we could deal with some of the challenges, but that had a drawback because our normal upwinding had a much lower accuracy than our basic scheme. Okay. Okay, and so last time what we talked about was a higher order scheme for finite differences. And where we left off was talking about a higher order scheme for finite volumes. Okay? And so for finite volumes for FEM, our higher order scheme is known as the quick scheme. Recall from last Wednesday, quick is the reason I write it in all capitals is that it's an acronym. Okay. So what the acronym stands for isn't as important as actually implementing it. Okay? But what makes the quick scheme unique is that we kind of have two different versions. Okay? The whole idea with higher order schemes is that, where we get our extra accuracy is that we kind of bring in additional neighbors into the computation. Okay? Because normally up to this point, when we do our usual kind of algebraic equations, we only bring in the immediate neighbors, right? The neighbor immediately to the left, immediately to the right, north and south. Okay? But by bringing in additional neighbors into the computation, we can make it more accurate. Okay? And so the quick scheme, we only bring in one additional neighbor. Okay. But then the question is, do we put that extra neighbor on the left or the right? All right, and so that led us to our two different versions. Okay, I'm not explicitly going to repeat kind of the example we did last time, but I'm going to kind of jump ahead to how we implement this in 2D. Okay, 2D, or say in 2D FBM. Okay. Remember, our main thing is that for each cell we have to evaluate 4 different integrals. So this is where things are going to get tricky, because for each of those integrals that we evaluate, each of those integrals are going to have two versions for quick. Okay. And so we're going to have 4 times 2. So we're going to have 8 different options that we are going to need to be aware of. Okay? So there's really no, nice way around it. Well, there is a nice way around it. I can just give you the general rules. But I think, for kind of where we are in the class right now and for how complicated this is, I think what's going to be more beneficial, especially, for those of you who are using finite volume for the final project, is for me to write out explicitly all 4 integrals with each of the 2 versions. So we're gonna have a lot of writing ahead of us for the next maybe 15 or 20 minutes. But hopefully this is going to be useful. Okay, so I'm going to write out all 8 kind of expressions that we need to do. Okay. All right, but that was just kind of mostly a recap from last semester. So before we kind of write our in-class essay, I guess, are there any questions before we get started with that? Okay, all right. So just to remind you, for each 2D cell, each cell that we have is a square like this, right? We're performing our integral, integrating around each side of the cell. So on the east side, remember what we're evaluating is this. Integral on the east side of phi e dot n hat minus k gradient of phi dot n hat. Yes. Okay. On the north side, we're evaluating the same thing. So integral on the north side of phi e dot n minus k gradient of phi dot n hat. Yes. Okay. South side, same thing. The only difference between these integrals is kind of the side that we're evaluating it on, and so hence the kind of the subscript for each of the integrals. On the west. Okay. All right. So remember, when we're doing finite volumes, we evaluate each of these 4 integrals individually, and then we add up their contributions at the end, and that's what gives us our algebraic equation. Okay. Okay. Well, under quick scheme, each of these going to have 2 different versions. What I'm going to do is I'm going to go through each side or each of these integrals and show you the 2 different versions of quick for each one, depending on the direction of the velocity. Okay, so let's start on the east. Okay, and so for the east, we have these 2 versions. So with both versions, we're going to have a delta y out front. And so let me go ahead and start with that. Okay. All right, so the first version is going to be u times minus 1/8 phi underscore w plus 3/4 underscore c plus 3/8 e minus k phi sub e minus phi sub c divided by delta x. So we use this version if u is greater than 0. And so if the x component of velocity, excuse me, if the x component of velocity goes from left to right, okay. right, so before I write the next version, let's kind of take a step back and kind of look at this expression and just kind of make sure that it makes sense to us, right? And so if u is positive, that means it's going from left to right, okay? And so the velocity is going this way. Let me draw a cell right here. Okay. And so remember, the quick scheme, at its core, it's still an upwinding scheme. And so it still kind of follows the same spirit as like our forward and backward difference that we used before, okay? And so just like our regular upwinding, we want to put the extra neighbor, we want to put the extra emphasis on the cell that's, to the left of this, right? Because that's where the upwind direction is. And for the east face right here, right? That's where we're evaluating this integral. That extra neighbor is going to be on the left. And so that's going to be the west cell, okay? So that's why you see this -1/8 phi underscore W here, okay? Or phi sub W, because we're putting extra emphasis on that side. Okay, so now let's look at the other version. And so the other version, we have a delta y, square bracket, u. So the coefficient values are the same. So, we're still going to have a -1/8 there. It's just that where we put the neighbor is going to be different. And so in this case, this is going to be the case where u is less than 0, so it's coming from the right. And so here we want to put the extra emphasis on the right here, okay? So we're going to put our extra neighbor on 2e, which is the distant east. Okay. And we also have our diffusion term as well. And this is the version if u is less than 0. Less than 0. The first one's greater than 0. The second was less than 0. Yeah. And so if you'll notice, because this is the east integral, phi sub e and phi sub c are always in there, right? So in both versions, we have phi sub c and phi sub e. Right? So these ones are always going to be there. It's just that, for version 1, we put the 3/4 on phi sub c, and in version 2, we put the 3/4 on phi sub e. Right? So, for the east integral, phi sub c and phi sub e are always going to be there. Just just how much weight we give it depends on the direction of the velocity. Okay. And then additionally, depending on the direction of the velocity, that tells us which extra neighbor that we want to put. So either we want to put it on the left or we want to put it on the right. All right. Any questions on this? Okay. All right. So let's do the same thing, but let's do it for the south integral next. We're going to follow the same logic here, except now, we're evaluating the integral on the south. Okay. This one we have a minus v times 1/8 phi sub 2s plus 3/4 phi sub s plus 3/8 sub c. Okay. In all of our expressions here, all different versions, the diffusion terms stay the same. So, there's less to worry about. We're only just focusing our quick scheme on the convection term. Okay. Okay. So that's the version if v is greater than 0. Now let's look at the version if v is less than 0. And so if v is less than 0, then we use that version where we put the extra neighbor up top. So that's why we have v sub n. So now let's do the West integral. So both versions will have delta y in the front. All right, so first will be the version if u is greater than 0. So first we have a minus u times minus 1/8. Plus 3/4. Plus 3/8 v sub c. Okay. And we have the version if u is less than 0, so we have a minus 1/8. V sub e plus 3/4. V sub c plus 3/8. Sub w. So that's if u is less than 0. Okay. So if u is less than 0, we put more emphasis on the right because that's where the velocity is coming from. And so that's why we put our extra neighbor on the east. Okay, so that's why we have a minus 1/8 v sub e. And all our diffusion terms stay the same. So in both versions, we have a k times v sub c minus v sub w, all divided by delta x. Okay. And then finally, we have the north integral. Like the others, we're going to start with the positive case. So if v is greater than 0. That version there is if v is greater than 0. And that's our final version if v is less than 0. So if v is less than 0, that means the velocity is coming from up top. And so we put our extra neighbor up north. And so that's why we have the phi 2n expression. Okay. Okay, so it's a lot of writing, I know. So I'll kind of pause here because I know people probably are still writing it down. But kind of while we're here, are there any questions on any of these expressions here? Yeah. You mean like the 3/8, the 3/4? Yeah. So those aren't arbitrary. So there is a proof that kind of shows that's what kind of gives you the best results. We're definitely skipping over that proof, but those coefficients are optimized for this. All right, and so let's go ahead and look at it an example then. And so this example is mostly code, and so there's not really much for us to look at in terms of the problems, just because as you can imagine, writing out algebraic equations with under the quick scheme is a big pain in the butt. And so the best thing is to kind of look at it in the code. But the good thing is that the way I've kind of presented to you here, again in terms of these coefficients, again in terms of these two versions. This lends itself really well with code, right? Because if you look at it, the main way that we choose between the two versions depends on the sign of the velocity. Right? And the thing is that when you're writing computer code, when you have kind of a very clear-cut case like this, clear-cut conditional, this is really perfect for an if statement. In fact, these expressions here have if in them already, right? And so what you'll see is that, I'll go over kind of one example of the one integral, how I implemented it. And then the rest kind of follow that same logic. But what you'll see is that this is kind of an exercise in if statements, right? And so if you like if statements, this is going to be great. If you don't like if statements, then, maybe, but, we'll try to work our way through the logic. Okay, so let me write down the problem statement before we jump into the code. All right, so for this problem, we're going to be solving the following equation. So we have 10 partial p partial x plus 75 partial p partial y is equal to 3 partial squared p partial x squared plus partial squared p partial y squared. Okay. So this is the example we did last time with finite differences, except now we're going to do it with finite volumes instead. Okay. And we're going to be solving it on the following domain. So this isn't a cell, this is the entire domain. Right? And so in reality, we're going to be splitting this up into finite volume cells, but just for simplicity, I'm just going to draw the squared domain. This is mainly just to show you the boundary condition. So we have p is equal to 50 up here. P is equal to 50 here on the left. P 5 on the right. And p is equal to 25 on the bottom. Okay. Let's write out the properties for this problem. So we'll assume that the length of each of the domain in each direction is going to be 1. So we have Lx, Ly is equal to 1. Our x velocity here is 10. Our y velocity v is 75. And our k is equal to 3. Okay, so that's our diffusion coefficient. Right. And so what we want to do is we want to write the code solve this using finite volumes. In particular, we're going to use the quick scheme for this one. And okay. So for this problem, so I chose a relatively simple problem just to kind of illustrate this for you. But of course, one thing that you may notice right away from this problem is that our velocities are fixed, right? And so our velocities, they don't really change with space, they don't change with time. I mean, this is a steady problem anyway. And so we know already from the jump that our velocities, both our velocities are going to be positive. So, right away, this kind of takes a lot of the drama out of the problem because, if you look at our quick schemes, right? All the different versions of the quick scheme depend on which direction the velocity is going to go. Okay. In this case, we know already what direction the velocity is going, and so we can kind of already pick ahead of time which version of the quick we want to use. So I'm bringing this up because we're going to be going, and so we're not going to do this, by the way. We're not going to do this in the code. I'm going to show you kind of a more general approach with the if statements that can be more general. Okay. But theoretically, if the directions of the velocities beforehand, there's really no need to go through all that. Okay. But the reason we're not going to do this is because the thing with code is that it's normally very easy to change the parameter values, right? And so I can go ahead, we can write this code one way, and I can say that, instead of v being 75, why don't we make it -25 instead? Okay. And that's usually very easy to do. So, especially with the way that we structure our codes, we just change the variable for v to be -25 instead. Okay. And so if we weren't using the quick scheme, that wouldn't cause any issues because up to this point, the direction of the velocity didn't really make a difference in terms of how we implemented our code. Okay. But it does cause an issue with the quick scheme, right? And so if we make kind of a very simple kind of seemingly mundane change like that, we'd have to overhaul all our code. So instead of using the top version, we'd use the bottom version instead. So, believe it or not, that's an even bigger headache. So what we'll do, instead when I'm presenting this code to you is I'm going to show you a code that'll work no matter which direction the velocity is going to go, because we're going to check. And so we're going to tell the program to check before you assign any coefficients. Let's check and see which direction the velocity is going, and then we'll choose the coefficients that way. Okay. But I wanted to bring that up just because, it can be. It's going to seem like we're going through a lot of trouble and a lot of effort for cases that aren't even going to happen. But it's always good when you can write your code in kind of a more general way to be more flexible and handle more situations. That's always a good thing, and that's the approach we're going to take here. Okay. Any questions on this? Okay. All right. So let me go ahead and bring up the code. Let me go ahead and share my computer screen here. And I should have brought this up beforehand, but just like last week, I was distracted by basketball. Lakers won, by the way. Crazy to think where their season started and kind of where they are now. Friday was a lot of fun.
Warriors.
I got the Lakers. Have to.
Yes,
Well, I can't say that, but I won't say no to that either. Okay, I choose to put it on here. In the chat. That's right, Lakers in 6. I didn't put here. First half, Sixers and Celtics, only 2 free throws have been shot. That's crazy. Sorry about this, guys. Did I not upload it? 2D advection diffusion, find a difference. Oh, here we go. Okay, so I'll link this code onto our week 15 page just so that you can see it. But okay, so here is the code, and so I will say this is probably one of the lengthier codes that we've gone over this class, and so we're definitely going to take a lot of time today to go over it. Let me make the font a bit smaller just to make it a little bit easier to see as well. Size 20 font is a little bit obnoxious. Okay, can everyone still read the code? Okay. 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 So this is the implementation of the quick scheme, right? And so section 1 here, section 1 is still mostly the same. We're just defining our variables. Okay. Section 2 is where we're going to be spending most of our time, right? So just like any finite volume code in 2D, we're going to visit every single cell. And so that's why we have our double for loop here. So our I and J loop. And so in this section here, we're computing the ID numbers. And so this is no different. Okay, so we have my ID, west, east, north, and south. And so these are all the immediate neighbors. Okay. But because this is a higher order scheme, we have to compute the further neighbors as well, the distant neighbors. Okay. So I call this west ID 2, east ID 2, north 2, and south 2. Okay. And so if you want to link this up back to our coefficients in our in our notes, this is phi 2w, phi 2e, phi 2n, phi 2s. Okay. Okay. Then we come to the code. And so, the way to kind of read this code is I kind of broke this code up into different integrals. Okay. And so if you read the comments here, each section kind of tells you which integral we're evaluating. And so the first one is the east integral. Okay. So this entire code block here from lines 39 to line 60, this is all just for the east integral. And then we have the same thing for the south integral, same thing for the west integral, and same thing for the north. So this is probably the most lengthy code that we've looked at. Okay, so let's go through the east integral and let's talk about all the if statements that are here, because then they'll, each one kind of serves a specific purpose. Okay. Okay. So let's look at the east integral first. And so remember, this is for an individual cell, and we're performing the east integral for that individual cell. And so I think the thing that's kind of confusing for this, especially for those of you who are doing finite volumes for your final project, is that all of the if statements that we just talked about, they're built on top of all of the other if statements that come with finite volumes as well. Okay. So I'll kind of do my best to kind of show you which if statements were there from before. So this was kind of previously from finite volumes versus the if statements that are new based on the quick scheme. Okay. All right, so let's walk through the logic here for this east integral. Okay. So this first if statement. Okay. First, we're going to check if I is equal to nx. Okay. And so what happens when I is equal to nx? And so what this means is that this is the case when our cell is on the very right side of the domain. Okay. And so when we're on the very right side of the domain, we have no east neighbor. So let me go ahead and add to this here. We have no east. Line. Okay. All right, and so if we're on the very edge of the domain, we have no east neighbor. And so the only thing we can do here is we can apply our Dirichlet boundary condition. And for this particular problem, our Dirichlet boundary condition is phi is equal to 25. Okay. And so you can see here that, when we have a Dirichlet boundary condition, these are the modifications that we make to the left-hand side matrix and the right-hand side vector. Okay. So these are the same as last time. So, there's not much really to say here. Okay. But just remember, with finite volumes, when we have the Dirichlet boundary condition, we still make modifications to the left-hand side matrix. It's just that they're modified for the boundary condition. Okay. And so this part right here, this section of the code, this right here is identical to what we've done before with finite volume. So this part's nothing new here. Okay. Okay. And then the way I've kind of structured this is that if we have a boundary condition, then we execute this part of the code, and then we end, because there's nothing else for us to do. Once we apply the boundary condition, then that's it. Okay. Okay. But for the case when we're not on the boundary, and so when we are not on I is equal than X, that means we have an interior node. And so from here on out, let me go ahead and enter here. From here on out, or at least until we reach the end of this integral, we have at least one E statement. So if we have at least one East neighbor, that means we can actually use that East neighbor and bring it into our calculations. Okay. Okay. But this is where things get a little bit complicated, because this is where the quick scheme kind of comes into play, right? And so the first thing we're going to check, okay, with this else if statement here, the first thing we're going to check is we're going to check the direction of the velocity. Okay. And so you can see here we're making an else if statement, else if u is greater than 0. Because if u is greater than 0, that means our velocity is going from west to east. That means that we're going to put more emphasis on the west side. Okay. And so, we're going to, put more emphasis on the west. Okay. All right. And so this if statement right here, together with this else statement right here, okay? Notice how these two are kind of have the same spacing in the code, right? So they're indented the same way. These two here, these kind of give us our two quick conditions, okay? Because if u is less than 0, then if u is less than 0, then we don't even go into this part of the code right here. So if u is less than 0, then we're strictly going into this part right here. Okay? So this part right here, this else if u is greater than 0, and this else, this is new. So this is unique to the quick scheme. Okay. Okay. All right. And so if u is greater than 0, then we know our velocity is positive. Okay. Then we jump into this else statement. Okay? And so from here on out, we want to put an extra neighbor. Okay. Because that's what the quick scheme is. And so the quick scheme is we want to put that extra neighbor, but we want to make sure that that extra neighbor is available. Okay. So here, we want to incorporate extra neighbor. Okay. And so we want to incorporate an extra neighbor to make our scheme higher order, but we want to make sure that that neighbor is actually there. All right, and so in the case when u is greater than 0, that means we want to put our neighbor on the left, right? So on the west. Okay. We haven't checked to see if we have a neighbor on the west. The only thing we've checked to see is that we have a neighbor on the east, right? And so what this if statement does, this if statement checks to see if we actually have a neighbor on the west. Okay. And so if I is greater than 1, okay, if I is greater than 1, that means we have a neighbor on the west. Actually, let me revise this. So if I is greater than 1, then we have a neighbor west, thus. Okay. And so if we have a neighbor on the left, on the west, then we can apply the quick scheme. Okay. And so you can see for the quick scheme, we have three coefficients. And so we have a coefficient for phi sub w, that is a -1/8 times u times dy. Okay. And then we have a coefficient for phi sub c, so that's 3/4 times u times dy plus k. And then the coefficient for phi sub e is a 3/8 times u times dy minus k. Okay. All right, so those coefficients are read off just kind of directly from our notes. Okay. Okay. But if we don't have enough neighbors for quick, so let's say that we don't have a west neighbor, from here we just kind of revert back to our basic scheme. And so that's what this is right here. So we have a 1/2 times u times dy on both the my ID and the east ID, okay, for both phi sub c and phi sub e, and we have a plus k minus k. Okay. So there's kind of 2 levels to check here. And so, first we have to check to make sure we have an east neighbor. If that's the case, okay, then we move on to our quick scheme. Then when we apply our quick scheme, we want to make sure we have our extra neighbor there as well. Okay. All right. So it was kind of a lot to take in. And so, you definitely, if you're, especially for the homeworks, and if you're doing this for the final project, definitely kind of go through this again, because it's tough. It's a lot to go through. So it's one thing, I think, to kind of stand up here and talk about it and to kind of write as many notes as you can, but it's one thing you kind of have to just talk the logic through yourself, because that's the only way to kind of. All right, any questions on this so far? Okay. All right, so let's look at the other version. And so if the integral is, if the velocity is negative, that means we go from east to west. That means we want to put our extra neighbor on the east. Okay. But the same thing is going to apply here. And so the same thing here is that we want to put our extra neighbor on the east, i.e. at 2e, but we have to make sure that the 2e exists. Okay. Okay, so that's what this if statement checks right here. So if I is less than nx minus 1, so we're basically one off the boundary and one more. Okay, that means we have a neighbor to the east. This checks if I is less than nx minus 1, we have a 2e. All right, and so in that case, we can apply our quick scheme, and so we have a 3/8 on phi sub c. We have a 3/4 on phi sub e, minus 1/8 on phi sub 2e. Okay. All those multiplied by u times dy, and then we have our diffusion coefficient as well, which is a plus k and minus k on phi sub c and phi sub e. Again, if we don't have enough neighbors for quick, then we just revert back to our basic scheme. So that's u dy divided by 2 plus k, and then u times dy divided by 2 minus k for phi sub c and phi sub. All right. So that was just one integral, and so it's definitely a lot of code. It's definitely a lot to go through, but as with any of these kind of posted codes that I give you, go through them slowly. Read each if statement, try to kind of understand what's going on, and it helps tremendously. Okay. Any questions on the east integral here? Okay. All right, so we have the same thing for the south integral, and so I'm going to go through this one a little bit quicker, just because it's kind of the same logic, but I think it kind of helps to kind of view it again. Okay, so for the south integral, first thing we need to check is we need to check to see if we have a south neighbor. Okay, and so if j is equal to 1, that means we're on the very bottom of the domain. That means we don't have a south neighbor. Okay, and so if we don't have a south neighbor, then we just apply the boundary condition. Okay. All right, so that's what this checks. And so if j is equal to 1, then we do not have a south neighbor. So we go ahead and apply our boundary condition. And so in this case, our boundary condition is a Dirichlet one, where phi is equal to 25. Okay. And then once again, we're going to check the velocities. And so we're first going to check if v is greater than 0. And so if v is greater than 0, that means we're going to put our extra neighbor on the south. Okay. And so if we're going to put an extra neighbor on the south, we have to make sure that it exists. And so we're going to check that. And so if j is greater than 2, that means we have, not only our south neighbor, but another neighbor to the south of that. Okay. And so that's what this code does right here. Okay. But if we don't have enough neighbors for quick, and so if we only have that one neighbor to the south, then we just revert back to our basics. Okay, so that's what this does here. And these coefficients are the same as the notes. And so definitely cross-check the coefficients, but I think that's the most kind of important thing. Okay, and so else, if we don't have enough neighbors for quick, then we have this here. Okay. The other case is if the velocity is negative. And so if the velocity is negative, that means we're going from north to south. Okay, that means we want to put our extra neighbor to the north. Okay. And so if we want to put our extra neighbor to the north, we want to make sure that it's there. And so we're going to check to make sure we have a north neighbor. If we do, we can apply our quick scheme. So we have our 1/8 minus 3/4 minus 3/8. Else we don't have enough neighbors for quick, and so we apply our basic scheme here. Okay, so that's the south integral. So that's kind of the whole thing, kind of the entire kind of logic of these statements kind of more quickly. Okay. We have the exact same code for the west integral, okay, and the exact same codes for the north integral. Okay. I will say, so when you're dealing with these kinds of codes and you're dealing with all these kind of coefficients and terms in the left-hand side matrix, I would say the most common mistake that people make is kind of with these IDs. Okay. And so it's tempting, it's very tempting, and I do this too. So when you have kind of sections of code here that look very similar, it's very tempting to say that I went through this trouble. I wrote the integral for the west, for the east integral. Let me just copy and paste that 4 times to apply that for the south, the north, and the west integral as well. Okay. And when you copy and paste, you know that I should change this to like the west. I should change this to west. I should change this to U. Okay. And so I think the most common mistake that I see people make is that it's tempting to kind of copy these big chunks of code for these integrals and just kind of make minor changes for the different sides. But make sure you're really thorough with that. So make sure you're really thorough in changing, everything that should be west, change it to north, everything that should be U, change it to V, and so on and so forth. Okay. Okay. And so that is that. So let me go ahead and run the code just to kind of show you what it looks like. And so the solution is going to look exactly the same as our finite difference code. Okay. Okay. So one added benefit of the quick scheme over our finite difference code is that this is actually upwinding, and so you have much less fear of instability. Okay. It's a lot of work. It's very complicated, and there's a lot of places where you can mess up. But if you had to ask my opinion, I think the quick scheme is a better scheme than our 4th order function. Just because it accounts for more things and it's more flexible. All right. Any questions on this code here? Okay. All right, so I'll post this code online, and so you'll have it. So I'll definitely do that when I get back to my office today. But that's basically the quick scheme. Okay. All right, and so with that, that's the end of the higher order scheme. So let me go ahead and bring back the iPad here. Okay. All right, and so with that, that is the conclusion of higher order. But, and so, what I wanted to say is that, that's everything you need for the final project. Okay? But that's not quite the case. So I want to make one kind of big note. I know a lot of you probably haven't reached this point in the project, but it's an important note to me. I know because some people are here. And so what we just went over was higher order schemes for steady problems. So there was no time marching, there's no delta T, there's no explicit U or implicit U. Okay. Final project. The final project is going to require you to implement a higher order scheme together with the time marching scheme. And I guess explicitly, there's only one time marching scheme you can use for the final project, which is implicit UA. Okay. And so that means when you apply a higher order scheme with the time marching scheme, the coefficients are going to be different. Okay. And I haven't given you those coefficients. And so part of the final project is to, do some calculations on paper, do some derivations on paper to derive what those coefficients would be when you combine these two. So I'll give you a hint. And so I'll give you a hint for finite difference. Just because we haven't gone over unsteady problem for finite volumes. That's kind of the next thing. But I'll kind of give you a hint on how to set it up. Okay. All right, so that's the equation for the final project. There's no source term, and so the final project doesn't have a source, and so that's kind of one nice thing to do here. Okay. All right. And so when you're deriving the coefficients, what you're going to do, just like we've done, I think dozens of times in this class, up to this point, is we're going to replace each of these derivatives with a finite difference expression. Okay? In particular, for these two derivatives, you're going to set these. You're going to plug in the higher order convection or the fourth order finite difference. So that's what's going to make this higher order. So you're going to take those two first order derivatives and apply our fourth order finite difference test. Okay. For these two, so for our second order derivatives, these are our diffusion derivatives. Okay. The good thing is that you can just apply our usual central difference here. So for diffusion, it doesn't change. Diffusion is the same in both. Then we come to the time derivative. So for the time derivative, and the good thing here is that you can also apply our usual forward difference in time. And so in fact, I'll give it to you. So this is phi comma j n plus 1 minus phi I comma j n all divided by delta t. Okay. So far, it's our usual technique. The only difference is that, we've applied our fourth order finite difference scheme to the convection derivatives. Okay. Next step. For all of these terms right here, okay. Remember, we're doing an unsteady problem. We have to assign either n or n plus 1 to these terms. And so for the project, I'm having you do implicit Euler. And so we're going to assign n plus 1 to all these features. So for all the spatial derivatives, remember, they all need a time index, but for implicit Euler, that is going to be n plus 1. Okay. I should number these steps. So red, this is step 1. Here is step 2. Orange here is step 3. Purple here is step 4. Step 5 is probably going to be the hardest part. So step 5 is going to be to rearrange these terms. And so what we're going to do is you're going to rearrange it so that all the n plus 1 terms on the left-hand side of the equal sign, and all the n terms are on the right. Okay. That's going to take a bit of algebra, so definitely take your time with that. All right, and so after you do that, most of your terms in your expression should be on the left-hand side. Okay. And you can do some simplifications here too. So I think usually what we do is we multiply by delta t, we divide by delta x. It doesn't matter all too much. Just just kind of be consistent with your work. Okay. All right, and so step 6, on the left-hand side, find all the like terms in terms of phi. Okay. And so you're going to arrange it in terms of the left neighbor, the right neighbor, 2 left, 2 right, up, down, so on and so forth. Okay. Then once you do that, you're basically done. And so at this point, the coefficients in front, each phi term, go into your code. Right. So I wanted to make sure that's clear because in the past, I've kind of done this, and then people start working on the higher order code, and then they basically just kind of copy the coefficients from the lecture. So I want to make it clear that for the project, I'm not giving you the coefficients for higher order combined with time marching, because I want you guys to derive that. Okay. And the way you can check, and so, for this particular project, I kind of chose it in a way where your basic scheme result should be basically the same thing as your higher order scheme, okay? And so when you're developing your higher order code, I mean, first thing you should do, you should get the basic schemes to work. That shouldn't be too much trouble. So that maybe like a day or so of coding, and maybe you asked a few questions for me as well. Okay. Once you get your basic scheme working, that's going to be your point of reference. And so when you start to develop the higher order scheme, you should try to get your higher order code to give you a result that looks like the basic scheme. Okay. All right, but that's basically kind of the process that you're going to go through for the higher order code. Okay. And then for those of you doing finite volumes, you're going to do basically the same thing, but with the quick scheme. All right, any questions on this part here? Okay. All right, and so for the last 10 minutes today, let's go ahead and start the last set of lecture notes that I have for the class, which is going to be time marching schemes together with finite volumes. All right, so this is our last set of lectures, one of our last order of business. Okay. And so just like finite differences, this was kind of the last thing we did with finite differences as well. So we're kind of just following the exact same path with finite volumes. Okay. So remember, unsteady problems are ones where we have the time derivative. Okay. Everything we've done with finite volumes up to this point have just been purely steady. So there's been no time derivative. Okay. So just like just like we always do with finite volumes, and so eventually what we're going to do is we need to integrate this on the cell. Okay. We're going to have terms that look like this. Okay, so I'm going to show you the 1D case first. We're going to take the integral of partial phi partial t dx. Okay. And so the good news here for us is that unlike all the previous derivatives that we've been going over in finite volumes, this integral is between, a time derivative, and the integral that we're performing is a space integral. Okay. And so the good thing is that these two things don't interact. And so for all intents and purposes, because this is a time integral, or time derivative, sorry. All intents and purposes, when we integrate over space, we basically treat this as a constant. And so our integral, the way we're going to perform integral is just that we're going to treat it just like the source term. And so we're going to apply trapezoidal rule. So what we get in the end is we have partial phi partial t evaluated at the centroid of the cell. X. 2D. In 2D, we have a double integral of partial phi, partial t, dA. Okay. So once again, we're integrating a time derivative over space, and so there's really no divergence theorem. There's no kind of fancy thing we have to do. So all we have to do is just apply trapezoidal. So what we get is partial phi, partial t, evaluated at the centroid of the cell, by delta x, delta y. Okay. And so what that means is that, all of our previous methods, so all of our previous techniques for time marching, explicit Euler, implicit Euler, we can apply this here as well. So there's not really, we spend a lot of time learning explicit Euler, implicit Euler. The good thing is that we can reuse a lot of that knowledge here. And so this means that, for our time derivative, we can just use our usual forward difference in time. And so we're going to have partial phi, partial t, evaluated at the centroid is equal to phi sub c at n plus 1 minus phi sub c at n, all divided by delta. All right. And so that's all there is to it, to time marching. So, next time on Wednesday, what we'll do is I'm going to do 2 examples. So I'll do an example with explicit Euler. We'll do that in 1D. That should be a fairly quick example. And then we'll spend most of our time doing a 2D example with implicit. Okay. So this is probably our shortest lecture notes, just because we've done time marching before. A lot of it's just combining it together with our knowledge of finite volumes. All right. Any final questions for today? Okay, all right, so I wanted to end class just a little bit early just to give you time to pick up your exam. So I have the exams up here, so you guys can come pick it up. So the average on the exam, remember, was 39 out of 50. So, very solid average. You guys did well. So go ahead and pick it up. Take a look at your score. Your score should already be on Canvas as well. Take a look at the feedback I gave you. And if you have any questions or have any, if I made any mistakes, just let me know, okay? All right, you guys go ahead and And thank you everyone for coming, and hope you guys have a good rest of your day. Victor, are you in class today? He is not. I'll bring the exams on Wednesday again too. So if you're not here, you can pick it up on Wednesday, or you can come to my office. Then you can pick it up there. Yeah.
Lots of right now.
Hmm?
The game is really.
Oh yeah.
Yeah. It's like
Joel's not playing today though.
not even like 1 minute, like 5 point difference.
Dang, Arden went off today.